Hello there and welcome to Yggdrasil, the brand new channel about machine learning and machine learning models productionalization. My name is Santiago Rincón and I work for the Spanish startup MLOps as machine learning operations engineer, which brings us to the topic of this video. It has been quite a buzz lately in machine learning community about machine learning operations, and I think it's worth to gain more understanding on what it is. In order to do so, and to realize its revolutionary potential for the industry, it's necessary to dwell on the importance of time. Theophrastus, some Greek philosopher, said that time is the most valuable thing a person can spend. Furthermore, human resource cost can represent up to 50% of the total cost of projects. Consequently, making the most of developers' time is crucial to the success of any company. Another concept to focus on is production deployment, which consists of bringing the development of technical teams to an environment where it delivers business value, where it gets actually used. It provokes a lot of memes in the community because it's often a black hole that drains time and only spits out frustration. This is especially true in machine learning projects, where developers are usually data analysts, which is a completely different field of knowledge from what is needed for that deployment. This is causing growing alarm in the sector, which is revealed in catastrophic headlines and in the fact that in practically all the job offers received by those of us dedicated to machine learning, and certainly in all the best paid ones, one of the essential requirements is to have knowledge of how to take machine learning models into production. This goal in software development is achieved thanks to the set of practices known as DevOps. However, although the underlying principles are the same, this set of practices is not directly applicable to the development of machine learning algorithms because there are essential differences between software development and machine learning system development. The first essential difference is what is made available for the business, its final product. What software development produces is a piece responsible for performing some task. In the case of machine learning systems development, on the other hand, a recipe is produced, a series of steps to be followed in order to obtain a predictive model. I'm aware I'm using concepts like predictive model that may not be fully understood right now, but we will deep dive into them in a moment, so please just some patience. The second difference is how the development itself is performed. Software development is similar to building, while in machine learning it's more like experimenting, like testing possibilities and extracting information from those tests, from those experiments. The last one is how the product grows. If we talk about software, the growth is cumulative. We have more and more pieces, we have more and more code, and it takes care of more and more responsibilities. If we talk about machine learning, it's substitutive. Each time we will have a better recipe, we hope. But each new recipe will replace the previous one. Bringing together practices that try to apply DevOps principles to the particularities of machine learning results in what we know as machine learning operations, or MLOps in short. To continue our journey, it's necessary to understand what the development of machine learning systems consists of. The good news is that it's an easy task because it's similar to experimental cooking by establishing a series of correspondences. In the development of machine learning models, we call value proposition the flavor we want to achieve, what we are looking for with the development. Whether this is predicting the animal that appears in a photograph or the probability that an internet user will click or not in an advertisement. Just as in experimental cooking, we measure the saltiness or the bitterness to see to what extent we have reached the taste we were looking for. We will have to establish some metrics, some key performance indicators that will allow us to judge to what extent we managed to provide the value we wanted to. The following concepts are related to data and the use we make of that data. We call training datasets to those that we use, as the name suggests, to train, to prepare our recipes. They are our ingredients. We will also reserve part of the data to act as tasters. We will use them to calculate the KPIs, the metrics we talked about before, thus measuring to what extent our work is being effective. Finally, we need to talk about the concepts related to the word model. 3 different things are usually called models, so when it comes to this word, it's important to be clear about what it refers to. By type of model, we mean the type of recipe. It can be a neural network model, it can be a probabilistic or Bayesian model, or to put it other way, what we want to do with our ingredients may be to grill them, or to bake them, or to boil them. Secondly, when we talk about algorithm, also very often called model, we refer to the set of defined operations that we do with the data to train something capable of predicting. It will be the recipe. Concrete instructions on what to do with our data, with our ingredients, to prepare a cooked dish. That cooked dish, that's something capable of predicting, is what is called trained model. And just as cooked dishes lose quality over time because the ingredients we use to prepare it deteriorate, the trained model degrades over time because the data used to train it becomes outdated. But it is enough to cook it again using new ingredients, using new data, with the same recipe, with the same algorithm. The fact that the trained models degrade is very important because it's the reason why the product of the development of machine learning systems is not the trained model, but the algorithm. As for experimental cuisine, the product is not the cooked dish, but the recipe. Now that we understand the basic concepts of model engineering a little better, let's give a little tour to the different tasks that need to be performed to achieve Ramsey-worthy dishes in our restaurant, following a developing loop known as CRISP MLQ. This development loop belongs to machine learning operations realm. To go through the loop, we are going to assume that we already have a model in production, providing value to the business. The first thing to do is to test different options, different models, different recipes. To do this, we will try different types of model, we will customize them in different ways, and we will prepare the training data in different ways. We call this experimentation. Then we will have to test them to find out which ones work better. And if they get the taste we are looking for better than the recipes we already have in the menu in production. If the KPIs or the metrics of our experiment are particularly good and better than those of the model we already have in production, the time will come to replace that one with a new one. This phase in which we decide to go ahead or not is known as validation. To achieve business value or winning experiment, we will have to take the recipe from our laboratory to the kitchen and start preparing dishes with it. This is the crucial and terrifying deployment of the model in production step, which we talk about in the beginning of this presentation. Finally, it's very important that we keep an eye on the behavior of our trained model to detect when it starts to decline and retrain it, and to identify its weaknesses and improve them in the next experiments. We call this monitoring. Let's go a little more into each of these phases with a concrete example. The first step, as we have already mentioned, is experimenting, which itself can be divided into 3 sub-steps. The first thing we will have to do is defining the experiment. For this purpose, we will decide and we will document our value proposition, let's say to predict if a user will click or not on an advertisement. The KPIs, the metrics, we will use to check if we are achieving the value we wanted, with what maybe the accuracy rate and the recall, maybe. The definition of the data we will use to train and validate. Let's say we decide to use data from a specific campaign, and then the separation of that data into a training set and a validation set, subdivided in turn into validation and test sets. We will say later why this last subdivision. Once we have defined the experiment, we move on to data engineering. First, we will analyze the training data. Then, depending on its characteristics and the value we will have set out to provide, we will decide on the type of model to use. Let's say we decide to try a neural network. The third step will be to get rid of the data that may confuse our model, either because they are incomplete, biased, or because they are strange cases. For example, if almost all our data come from Spain and we have one single connection from Australia, we may want to discard that connection. Finally, we will transform the remaining data so that it have the format and information accurate for the type of model we have chosen. And then we arrive to our last subtask in this phase, which is model engineering, where we will prepare the type of model we have chosen, the neural network in this case, for our specific case. Once done, we will train the model to obtain a trained model. With this experimentation phase completed, we are about to enter the validation phase. We enter this phase already having an algorithm, the set of transformations and operations by which to obtain a trained model from the training data, and a trained model. Recall that the objective of this validation phase is to measure how well our experiment has gone. We do this in two subphases. The first one is the validation itself, in which we use the first part of the validation data we separated in the experiment definition phase to measure the trained model effectiveness by calculating the metrics, the KPIs we have established also in the experiment definition phase. Let's say we achieve an accuracy rate of 60% with a 10% recall. Clearly, these are not good metrics, so we will go back to the experimentation phase. We will make changes and then we will be here again. Let's say we get an 80% accuracy rate with a 90% recall. Now we think these are good metrics. So we move on to the next validation subphase, which is the test phase. In this test phase, we will do exactly the same as in the validation phase. Calculate the KPIs, the metrics on the trained model, but we will use as testers the test dataset, which we have never used for anything. This is very important because we need the testers in this subphase to be this novel to emulate what we are going to encounter outside the lab. Let's say we get now a 77% accuracy rate with a 89% recall. To decide if these are sufficient metrics, we must compare them with those that we have from the model in production. If they are worse, we will completely discard the experiment and we will have to start defining the next experiment. If they are better, the model has earned the right to become the one we use in production. It's important to note that once we move on to this test phase, we can no longer continue with the experiment. We can only take it to production or completely discard it in order to keep the test data to be used exclusively as totally new data. Now we have passed the validation phase. We have reached the end of the blue wheel. We have done experiments, we have validated those experiments, we have done more experiments, we have validated them, then we have got metrics that are good enough to enter the test phase. In this phase, we may have decided to discard the complete experiment and we will be back to the square one, to the beginning of the blue wheel, and we will start defining the next experiment. Let's say that's not the case, but we have a model that improves the one we already have in production. It's finally time then to enter the yellow wheel, to enter the production environment. And to do so, the first thing we will have to do is to take our algorithm and apply it to obtain a trained model with production data. We will no longer use a single campaign as we did in the experimentation phase, but we will use all the data with a certain maximum antiquity, for example. Then we will start using this trained model to bring value to the businesses. For example, by using its predictions to better plan advertising campaigns. We will not now go into the difficulty of this last task, which is enough for a presentation on its own. Now we're in a beautiful moment. After all our work, after our experiments or validations or experiments or validations or experiments or validations, after entering the test phase and then deciding to keep the experiment because it improves the one we already had in production, after training the algorithm with production data and exposing it to use it, we have a model in production. We are predicting whether users will click or not in our ads, and it's not something theoretical. We are actually using it. We have avoided that black hole that can be the deployment in production. But let's not be complacent. We are not done yet. Recall that the trained model loses effectiveness as the data used to train it lose freshness, so it's necessary to control that. To do so, we enter the last phase of our cycle, which is monitoring. To control the trained model, we will test it from time to time. We will use new data, and we will use it to calculate the metrics, the KPIs, when we define the experiment, as we did in the validation phase. If they start to worsen, we will go back to the beginning of the yellow wheel, to the model deployment phase. We will regenerate a trained model with new data, and we will re-expose it. In addition, these tests will give us information on how the model is performing and how to improve that performance. For example, we might observe that it behaves particularly badly at night. This information enriches the definition of future experiments. And now we are back to square one. We are here again, but we have improved the algorithm that brings value to the business. By repeating this process, we will relentlessly improve the algorithm that brings value to the business with new experiments that we will validate and do more experiments and validate and test and decide to discard or go into production with the training of the models with production data, the exposure of those models, the monitoring and the retraining and re-exposure of those models. The two wheels won't stop spinning. The blue wheel will allow us to find new and better recipes, while the yellow wheel spinning will increase the reliability and the resilience of the algorithm that is bringing value to the business, since it will update itself. These two wheels rolling continuously allow us to continuously and rapidly improve the algorithm we have. And they give me an excuse to sing along with Chamillionaire. They see me rolling, they hate it. Okay, so through all the development cycle that we have covered, it's necessary to always maintain a series of principles, which are largely shared with DevOps. Some of those principles we have already mentioned on foresaw, but it's worth doing a final review and engraving them in our minds. I cannot overemphasize the importance of these principles. The first one is the continuous integration, delivery, training, and monitoring, as all the processes should be in a continuous loop. Once again, they see me rolling, they hate it. It corresponds with DevOps continuous integration and deployment. The second principle is that must be an iterative and incremental process. Even when recipes are substitutive, we must achieve an incremental improvement. To do so, it's important to never repeat experiments and to exploit the ones we perform as much as possible. To achieve this principle, we have some more principles. The first one is reproducibility. That means that we must be able to go back to any experiment and obtain the same results to enable the process to be incremental. To achieve this, we need experiment tracking, which means to keep track of all performed experiments to be able to extract all possible information from them. And we need version control, not only of the code like DevOps commands, but also of the pipeline, of the data, and of the metrics. The next principle we have to cover is automation. Nothing should be done manually if it's possible to do it automatically. This is a quite general principle. It may be applied to almost any task and it rarely fails. I am personally a huge automation fanatic. Then we go into the next principle, which is testing. Data, model, infrastructure, all must be tested to rapidly address any reliability problem, and it corresponds with DevOps quality assurance. we have to talk about two more principles. The first one is monitoring, which means keeping track of how production performs. It's a whole phase in the CRISP MLQ loop we have already covered. And the last principle, which is modularity. To be able to scale up and to achieve the desired looping speed, everything should be divided into small interchangeable pieces. This principle is also shared by DevOps. I hope you are not too tired. You'll be glad to know we are done. Now, if anyone asks you what a machine learning engineer does, what a machine learning operation are, or why anyone should care about that, I hope you can answer. In case you are not actually happy to know we are done and you want to investigate further, I will leave you with a list of assorted sites where you can learn more. It's the one you see on the screen, which is there, I think. You will also find this list in the video description. Best regards and see you in the kitchen!